Now for a short video on Newton's laws, talking about the three laws of motion and the law of gravitation, two factors that affect gravity. Newton is considered to be the father of modern physics and a math genius. And on the physics side of things, there are a few laws that he is very well known for and are taught in all physical science or physics classrooms around the world. First one's to look into the laws of motion, and these laws of motion do explain how and why objects move and allow us to predict the motion of objects. A lot of times teachers will tell students when they're trying to learn something new, it's difficult, that they think is easy. They might say this is not rocket science. Well, this is rocket science. This is how scientists are able to predict the motion of planets. This is how scientists are able to predict the paths that satellites and rockets are going to follow. This allows us to predict the motion of almost all moving objects. First law is called the law of inertia, because that's what it's all about. Inertia is the tendency of an object to resist changes in motion. Something that has a lot of inertia doesn't change motion easily. Something that has very little inertia does change motion pretty easily. So, for example, something like a train has a lot of mass, very large object. It has a lot of inertia. It's hard to speed it up. It's hard to slow it down. It's hard to turn a train. Something that's small, like a bicycle, has a lot less inertia. It's got a lot less mass. It's a lot smaller object. So it's easier to speed up. It's easier to slow down. It's easier to turn than the train is. Velocity also affects inertia. Things that are moving slow have less inertia than things that are moving fast. Think about a baseball. Somebody lobs a baseball at you underhanded. It's moving rather slow. Doesn't have a whole lot of inertia. Easy to stop, easy to catch. But if they throw the baseball at you as hard as they can, it's moving much faster. It has much more velocity. And as such, it's harder to stop. It's harder to catch when it's moving quickly. All because of this inertia. The first law states that objects' motions will remain constant in the absence of a net force. That this inertia will cause it to do whatever it's going to do, unless a net force acts upon it. So if something's moving, it will continue to move, unless there's some outside force. If something's at rest, it's going to stay at rest. Again, unless there is some outside force. In this illustration, this picture, there's a wagon rolling down a ramp hitting a block. And you notice when the wagon hits the block, everything that's stacked inside that wagon continues to move. This is because of their inertia. They're objects in motion. They want to stay in motion in the absence of external forces, if there is no net force acting on it. The second law of motion is called the law of acceleration. As you recall from the last unit, acceleration is a change in velocity. Acceleration can be speeding something up. Acceleration can be slowing something down. Acceleration can be change in direction. What the second law does is tell us what is going to cause this acceleration. And it says, when a net force is applied to an object, it will accelerate in the direction of that force. Pretty common sense kind of law. It says, if I push something with a net force that way, it accelerates that way. Pretty common sense. There are some things, there's little nuances about it that can make it a little trickier. Like if we apply a force in the direction that the object's moving, it will speed up. If we apply a force in a direction opposite of motion, it will slow down. And an idea called centripetal force that we'll talk about in just a moment. First, a simple illustration of the second law of motion, the law of acceleration. Here the space shuttle is blasting off. There are two forces that are working against that forward motion. We have the weight of the rocket pulling down, gravity, and we have air resistance, or air friction as they label it on this one, air resistance pulling backwards on it as it moves. Again, remember, air resistance occurs anytime something moves through a gas, like the atmosphere. It's got to push all this air in front of it out of the way, and it's got this low pressure that develops behind it, kind of like a wake that sucks it backwards. There's air resistance and gravity working against this rocket. But if the engines can produce a force that is stronger than these two, if the thrust of the rocket is stronger than the weight of the rocket and the air resistance on that rocket, we will have a net force upward, and the rocket will accelerate upward. Since the rocket is moving up and the net force is in the same direction, again, if the net force is in the same direction as the motion, the rocket will speed up. So it will accelerate by gaining speed, by increasing speed. That little nuance that I mentioned was centripetal force. And we have to remember that acceleration is rate of change in velocity, and velocity is speed and direction. So a change in direction is acceleration. We call any force that causes an object to change direction centripetal force. And the way I always remember this is centripetal force has the word trip in the middle of it. When I trip, I change direction. I was going that way, now I'm going that way. Tripping causes you to change direction. Centripetal force causes an object to change direction. Here we have a looping roller coaster, and as that roller coaster goes through the loop, the track produces a centripetal force towards the center of the turn. The track pushes this direction, causing the train and you inside of it to change direction right along with it. Now, interestingly enough, when you go through these curves, when you go through these loops and roller coasters, you feel like you're being pressed downward in the seat, but it's really the other way around. The seat is being pressed upward into you. You have inertia. Your body wants to continue moving in a straight line. But that seat comes along and pushes into you and changes your direction. That seat produces this centripetal force that pushes you into the curved path. Interesting and different way to think about riding a roller coaster and changing direction. The third law of motion, the law of action-reaction forces. For every action, there's an equal but opposite reaction. This is the one that students can most often recite, but most often don't understand. What it tells us, if I push on something, it pushes back on me with an equal size force in the opposite direction. And I have several examples that I pulled off the internet here. This is a car, and it's moving in this direction. For the car to move in that direction, the tires have to push backwards on the road. The tires are pushing in this direction. The road pushes in the opposite direction, making the car move. This is why cars don't work well on icy roads. When the road is icy, you can't get a strong reaction force. When the road is icy, the road can't push back, and it makes it hard for the car to move. Again, this is rocket science. When a rocket pushes the exhaust gases backwards, the exhaust gases push forward on it. It's that forward push from these exhaust gases that make the rocket move. It's a common misconception. When you watch a rocket blast off, you see all the fire, you see all the smoke pushing against the ground, and some students think that this exhaust has to be pushing on the ground to make the rocket move. And that's not the case. If that were the case, rockets couldn't move in space. All they have to do is throw something out the back, in this case the exhaust gases, and whatever it pushes out the back will push forward on it. In this example, we have a person pulling on a spring. He's pulling on the spring in this direction, so the spring pulls back in the opposite direction. It's that resistance that you feel when you pull on the spring. This one's a little harder to understand. This actually gets us into our final law of Newton's, the law of universal gravitation. Earth pulls down on a ball, but at the same time the ball will pull up on Earth. This is gravity in effect, and it actually shows a two-part force. And for many students, they don't understand that gravity is a two-part force. Law of universal gravitation is another law of Newton's. It tells us gravity is an attractive force between two objects. The Earth does pull down on everything around us, but at the same time, all those things around Earth pull up on it. So if I jump in the air, yes, Earth does pull down on me, but at the same time, I pull up on Earth. Which always brings up an interesting question then. Why do I have to fall back down to Earth? Why doesn't Earth rise up and hit me in the feet? The answer is Newton's first law. It's inertia. The Earth has a lot more mass than I do, and as a result, a lot more inertia than I do. So it's harder to change Earth's motion. Really easy to change my motion, so I'm the one that ends up having to fall back down. But it is a two-way force. Now, the law of universal gravitation tells us that this gravitational force is affected by two factors, mass and distance. When looking at mass, you're looking at the mass of the two objects involved, so you and the Earth. Your combined mass is what produces the mass part of this, what the equation is. And then the distance between those two objects. The greater the mass, the stronger the gravitational force. So there is a gravitational force between this pen and me, and when I put it down on the table, there is a force that is trying to bring the two of us together. But it doesn't happen. It doesn't fly up and hit me in the face, because when I look at the combination of masses, I look at my mass plus the pen's mass, versus my mass plus the Earth's mass, the Earth combination wins. So the pen stays put. There's a stronger force there. Distance has the opposite effect. We say it's inversely related. The greater the distance, the weaker the gravitational force. So the further from Earth we go, the weaker the gravity gets. I have a guaranteed weight loss program for anyone because weight measures the pull of gravity on an object. If you want to lose weight, you've got to lose the gravity. The easiest way to do that is to get further away from Earth. So if you want to lose weight, join NASA. Become an astronaut because the further away from Earth you get, the weaker Earth's gravity is going to get, and the less you're going to weigh. Problem with that, of course, is the whole mass issue. Your mass won't change. You'll still be just as big as you were before, but you will weigh less the further away from Earth you go. That's about it for Newton's laws, and yes, it is a very oversimplified approach to it, but again, limited to 15 minutes or less. That should be enough to get you going.